Let's do an example for this section of the notes. First, let's read this example. We've got a rigid insulated tank with a paddle wheel that's filled with water. It's initially a two-phase liquid vapor mixture at 20 psi, consists of 0.07 pounds of saturated liquid, 0.07 pounds of saturated vapor. The tank contents are stirred by the paddle wheel until all of the water is saturated vapor at a pressure greater than 20 psi. We're going to ignore kinetic and potential effects. We're going to find the volume occupied in cubic feet. We're going to find our initial temperature in degrees Fahrenheit, find our final pressure, and we're going to find work. Okay, so let's go through and make sure we've got all the keywords here. We've got the word rigid. If y'all remember from before, that means we can assume volume stays the same. We've got insulated. Usually if you see the word insulated, that means you can assume that you can ignore any heat transfer from the surroundings. So that tells us Q is equal to 0. Right. Now initially we've got a two-phase liquid vapor, tells us the pressure, gives us the mass, so it's 0.07 of saturated liquid and 0.07 pounds of saturated vapor. And then it goes on to tell us eventually all of the water is saturated vapor, and it gives us this pressure, right? So we're greater than 20, and then we ignore these two things. All right, so those are the key points there that we need to pay attention to when we're working through this example. So let's look at this and see what we need to do. Kind of move this around a little bit here. Okay, so we're starting out with a pressure of 20 pound-force per square inch. The mass of the saturated liquid is 0.07, that's in pounds, and then the mass of the saturated vapor is 0.07 pounds. Now we're wanting to find volume first, so we want that. That's what we're looking for, a capital V with the bar through it. Now the way we're going to find that is to use specific volume. So let's go through this process and you'll see why that is. Now first let's look at quality. We've got 0.07 here, 0.07 here. Now for quality, remember you're going to put the amount of vapor in the numerator and then you divide it by the total mass. So here the total mass is going to be 0.07 plus 0.07. So obviously quality is going to be 0.5. And you could have determined that just by looking at these numbers. It's half and half, right? So quality would give you 0.5 because it's 50% vapor. Now that we've got this established, if you remember from before, we wrote down that volume has to equal the mass of the liquid times VF. So this is the specific volume, saturated liquid, plus the mass of the vapor times Vg. Remember, Vg is where we are 100% vapor. That's the specific volume at that point. Now what we need to do is find these specific volume numbers. So to do that, you're going to go to the table, and in the Moran book you're going to go to table A-3E. We have English units now, so we're going to go to the English version of the table, and if you go to those tables you'll find VF, that's going to be 0.01683 cubic feet per pound, and then Vg is going to be 20.09 cubic feet per pound. Now we already have our two masses. Now we've also found these specific volumes, So we're ready to plug everything in. So our volume is going to be 0.07 pounds times 0.01683 cubic foot per pound plus 0.07 pounds times 20.09. And I'm out of room here. Alright, so now we have that. Now check your units, make sure they all work out. Pounds cancel out in both of those terms, and we're left with cubic feet. Cubic feet is a unit for volume. So that looks perfect. Do the math here, and you get 1.407 cubic feet. So that's the volume occupied by that water that we've got in our system. Okay, point B, or not point B, part B, we want to find the initial temperature. So our initial temperature, what we want to do is we need to pay attention to the fact that initially our pressure is given, because we were told that initially we had a two-phase liquid vapor mixture at 20 psi. Alright, so pressure is known. So it's 20 psi. And we also know that we have a liquid vapor mixture. So with that, we know we can use the saturated water table. To get our information. Okay, so we're going to use table A-3E in the Moran book. Now, if you go into that table and you look it up, you can get your temperature value. Looking at this table, here's A-3E right here. We're going to find our pressure. Our pressure is 20. So here we are at 20. We come over here, the saturation temperature is 227.96. And this is the temperature we are at initially when we have that liquid vapor mixture. So that is the answer for B. So T1 equals saturation temperature, which was 227.96 degrees Fahrenheit. And again, we know that because we were given that temperature, that pressure, I mean, and we were told we had a liquid vapor mixture. So that means we have to be at this temperature. Now on part C, we want to find the final pressure. Remember, our mass is constant, so we have a closed system here, and volume is going to be constant because we have a rigid system. If both of these things are constant, then that means specific volume has to be constant. And now the final state, if you go back to the problem statement, it tells you that the contents are going to be stirred until all of the water is saturated vapor. So that means if we look at this on this vapor dome, state 2 is going to be all the way over here. Now if we were to draw a line here, that's the G point. So if we find the specific volume right here at this point, that has to equal V2. So V2 is going to equal VG. And that will come up in just a minute, so we'll find out. Now, let's look at V1 here. So specific volume 1. That's going to be volume over the total mass. So volume we already found, 1.407 cubic feet. Divide that by 0.14 pounds. That gives you 10.05 cubic feet per pound. That gives you specific volume 1. Now we already said that V1 has to equal V2 and V2 equals VG. So this means V2 equals VG, which equals 10.05 cubic feet per pound. All right. And we had to do it this way, go back to specific volume of state 1, because we don't know our final pressure. Okay, we have no idea what the pressure is. We just know that we go all the way to having saturated vapor. So that's why you just couldn't look it up in a table, because we don't know enough information right now to find that in the table. Now what we're going to do is now we will go to the table and we're going to kind of work backwards. We're going to go to that table A through E, and we're going to look in that table and we're going to figure out where we might be. So our VG number, or V2, was 10.05. So we're going to look in this column, the saturated vapor column, and we're going to find numbers that are close to 10.05. Now if we get really lucky, we'll find that exact number, but of course, you know, we're not going to find out. So we keep going down. We got 10.5, we got 9.4, but we don't have 10.05. So we're going to interpolate with these two data points. Okay, so we got 40, 45 for the pressure, and then we've got these two specific volume numbers. So we will do interpolation to get our final pressure. So we got pressure, and then we've got VG. So at 40, our VG number was 10.5. At 45, we had 9.4. Now you just interpolate. So we'll have 10.5 minus 9.4 over 40 minus 45. That's going to equal 10.05 minus 10.5 over X. Now, actually, let's not call it X. That gets confusing. Let's call this P2 minus 40. I don't want to get confused with quality. Now, all we have to do is solve this equation, and that'll give us our final pressure. And you get 42.05 pounds per square inch. Now, once you get that, you need to make sure that that value makes sense. So if we come over here, you look, it should be between 40 and 45. 42 is definitely between those, so that looks good. If we would have gotten a pressure of 83, for example, you would know something was probably not right. Okay, so always double check when you do interpolation, make sure it does fall in between your values that you have. It's a good way to double check your answers. Okay, and then now, what we're going to do is go to part D. This one we're going to find work. Now remember, anytime we're going to find work, you're going to have two methods. You have that integral equation where you have a change in volume and all of that, and you also have your energy balance equation. So we're going to go ahead and go to the energy balance equation. All right, so we got delta U equals Q minus W. We know here that Q is going to be 0, right? Because we said we had an insulated tank. So the insulated tank means we're going to ignore any sort of energy transfer by heat. Now this leaves us with this delta U equals negative work. Now delta U, this capital U, this is not found in the table. So we want to have the mass times specific internal energy at state 2 minus specific internal energy at state 1. And that's going to equal negative W. Okay. To fill in this equation to get work, we need the mass. We already know the mass, that was 0.14 pounds. We need to find these two internal energy numbers. Let's start with U2. For this one, what you're going to have to do is you are going to have to interpolate. And once you interpolate, you get 1,093 BTU per pound. So you're going to interpolate using this pressure value. All right, so I will leave that up to you guys to see if y'all can interpolate, get that value for U2. It'll be good practice for interpolation. And then for U1, remember when we were in state 1, we had a liquid vapor mixture. For that one, that exact value won't be in the table, so we do have the equation we can use though, where U1 will be equal to UF plus the quality times UG minus UF. Now UF and UG, those are found in that table A3-E. So you can find those and plug those in. So we'll write it down here. So UF is 196.19. UG is going to be 1,082. So these are from the table A3-E. Plugging those in, you get 196.19 plus 0.5 times 1,082 minus 196.19. And U1 then is 639.1 BTU per pound. Now we've got our two values for internal energy that we need. All we need to do now is plug into this equation here. Let's call this equation 1. All right, so for that one, let me get another piece of paper here. Let's go ahead and plug those numbers into equation 1. We're going to have negative work equals the mass, which was 0.14 pounds, times 1,093 minus 639.1 BTU per pound. Then you solve. Once you subtract these, multiply, and then divide by this negative, you get a negative 63.546 BTU. And this is going to be your work. Now this negative, remember that means work is done on the system. Right, so there's some external energy being transferred in by work that's going to make this whole process happen. All right, so hopefully that gives you a good example. We'll do examples using enthalpy and some of the other stuff in upcoming examples. All right, hope y'all enjoyed it. See you next time.